Okay, welcome back to the third lecture now from Convolutional Neural Network and Applications. So the last time in lecture 2 we really learned a lot about how convolutional neural network works. We applied it in practice with MNIST, and we have seen how JPUs these days really change the picture in terms of speed ups, in terms of speed, what we can really do. The lecture 3 will be uploaded as we speak, so it will be appearing very soon. So before we now basically look a little bit in our results, because some of you are still queued as I hear, some of you are not really having results yet, let us explore a little bit what we do in terms of applications. And I brought you a data set out of one specific domain, which is a remote sensing domain. Right? So the people that actually last week have been here already know a couple of these introductions, so what remote sensing is. But on the other hand, it's not only boring, it's also interesting, because we will compare now the SVM to our convolutional neural networks. So we will reflect a bit of what we had last week with a traditional classifier, like the support vector machine. And if you remember, we had also sophisticated cross-validation to get the accuracy very high. But still, we will see then later on, and hopefully tomorrow in the second part of it, when we talk about the CNN architecture for exactly that problem that we had last week, and see some specific aspects of it, like window tensors, and then do some practicals around it. So in a way, it would be really looking on the application field, what we have done traditionally in that application field with the kind of feature engineering that we discussed, and then really can have here in the second part the idea of using finally GPUs that we provided in Leuven with our scripts. However, we know from experience, this is an application field which is different from MNIST. I will make the case why that's also then, of course, much more computational expensive. Hence, the idea is not that you get out of a model here. We are not that quick with the K40s. Tomorrow morning, and this is the goal of the day, everybody should submit now, today, so that we basically can have a look tomorrow morning, right? So because we have kind of 40 participants, also using all the K40, which are available, will take some time in the scheduler. So overnight, this will be all scheduled, and when we all wake up tomorrow morning, we'll be back on lecture 4, there will be hopefully all of that computed. So that's the idea. So the end game today, having a really sophisticated data set, executing still on GPUs. So let's review a little bit the remote sensing application field. What is this about? It's largely about sensors that are, let's say, Earth observing. So it could be, for instance, a satellite. And this is, taking measurements of different spectral channels from the Earth. So it's not essentially, as you would think, just one image, right? It's generally that what the people think, it's just one image. In a sense it is, but because we have also the spectral channels, right, into the Earth itself, we call that basically different spectral channels, and a little bit explained here with different wavelengths of light emitted from the Earth, for instance. Here you speak then more about a cube, right? So in a sense, as a learning guy or as a machine learner, you would say, of course, you have the kind of spatial resolution here that you have always like XY coordinate in terms of pixels and the image, but you have another dimension here, which is essentially your feature vector, right? So you would have a channel, there are different bands on the satellite, and they today actually have around 220 bands, right, that they can measure. So you would have like 220 features. However, here and there the problem is they are like large overlapping and so on, so you have some problems in terms of noise again, right? So when we talk about this data set, keep that in mind. Of course, it's not as clean as you would think. It's, of course, a beautiful cube, but this cube is loaded here and there with lots of traps for doing data analysis. Right, so this is the idea of the kind of application field we go today, and I know it's the same we did last time. That's why there's a nice idea in terms of comparing it now with the automated feature engineering. So in order to do that, we have to go a little bit back to what we did last week. If you remember, we had, for instance, Rome, which is a nice example to show, also more or less a kind of smaller example with just here a kind of couple of classes, 9 classes really, with samples for training and test. And what the satellite is doing, it takes the image in different spectral channels, and we engineer the features here. So that's what one of my PhD students was doing a long time, also partly in parallel. But you end up with different, let's say, feature channels of saying red, green, blue, and maybe or possibly also add infrared of the same scene. And then basically already have, you know, some labeled data. That means someone was really going to roam downtown, so to speak, and actually creating labels and say, well, this pixel is water, this is a building, this is a tram, this is etc. You can see from that creating labels will be a very difficult thing. If you go to practice, perhaps in the job and so on, labeled ground truth is very costly. For instance, for this ground truth campaigns, you're sending people pixel by pixel to annotate, but the same thing you have seen in the neurosciences. The brain images are quite huge in terms of resolutions, and there to do kind of the ordering and kind of the labeled pictures and say by pixel, this is this particular Boltzmann region, this is this particular cortical area. You can imagine it take a long time, right? Hence, labeled ground truth is very rare and very precious. So you use this basically from the data observed, the ground truth that you get, and then you create your modern algorithm. That's something which basically have all of them together in the land cover types classification. So we want to find out what's actually on the ground. However, to do that, we applied feature engineering, and this is now interesting because we will not do that in the convolutional neural network, but it's a good way to contrast it now in a specific case, right? So here we use different, you know, mathematical morphology trees at certain places in time cut it, which means essentially the neighborhood of the pixel in different intensity values, and that should ring a bell when you think about how a neural network now learns. There's different feature maps in spatial, right, kind of very close relationships. So you see there's already a kind of close relationship of just not staying pixel by pixel, right? This differentiates here the land cover classification, for instance, that we see here, to the MNIST, right? So what is the difference? Maybe someone can tell about that. What's the difference between the MNIST classification problem and here the pixel-wise remote sensing? Huh?
Size of the images.
1 point, yes, yes, yes.
The number of output possibilities. So for the endless problem, we have 10 different clauses. Here we have way more clauses.
Kind of not really true. We have 2, 4, 6, 8, 9. So, but it goes in the right direction. Maybe another one.
For the endless, there's one label image, and here you have to add multiple labels to the same image.
Exactly. Now think about the classification problem inherently is very different, right? You have the whole scene in the MNIST, so to speak. The whole pixels all just contribute to one label. Very simple. It's a 0, it's an 8, it's a 9, right? And the gray intensities of all these neurons that we had learned in the CNN contribute to that, right? So here it's different. Here we don't want to say this is all Rome. That's not interesting. That's what we can do since long time ago, because there's a very beautiful river that is very clear in Rome and how it looks in terms of shape. We just need to actually do that. What we want to know is grand truths, you know, grand land cover studies really how basically the city changed over time, really on a pixel way. And with this you really are pixel by pixel saying different things, right? And this of course is much more now a different challenge that I want to stimulate with you. Of course the media is full of this scene classification of saying that's a dog in the image, there's an elephant in the image, but they are all pixels contribute to one label and saying that's a dog. That's not completely true. Newer approaches in deep learning also have this bounding boxes saying here's part of the dog, here's part of the cat, and having in one image of course more features or more aspects basically part of it, then this is of course more enhanced, but here's still very much specific pixel by pixel. Right? So we add a new complexity here just to show you another type of applications how you can do it. Right, when you do this feature engineering then, you end up basically with different dimensions of having new features. So we created new features, which is very nice. So we don't stick basically with just what's happening here on the satellite. We create our new pictures. so to speak, on ourselves, based on different grayscale and so on, panchromatic images. So there are lots of ways how you can do it. Essentially, by the way, what I was saying is it's a manual process partly supported by automation. Right? And now we want to change how the situation changed in remote sensing when we don't do any of that and just throw it into a training phase. Right? Here, the example that we had last time was, for instance, a support vector machine, which is a very robust classifier still. So just because deep learning is there doesn't mean we stop now using support vector machines. It's a very sophisticated model and has accuracy in many ways and is a very kind of easy trainable models. If you remember, we did the grid search the last time together, which was essentially just 2 parameters, right? The kernel parameter and also the cost function for allowing errors. With this, is of course very nice to optimize. Still, we have seen convolutional neural networks can do a hell of a lot of things. So let's go a bit forward. Here you can add high resolution panchromatic images. You basically work on the features. You think what can improve the classifier, and you manually do that, basically based on different data items, so to speak, in order to create your feature vector, right? And the feature vector in the end is the one you give then to the classifier. So it's not new to you for those at least that have participated last time, right? And of course, always remember we have a really rare number of training examples, so we're not swimming in data like an ImageNet. We have seen 40 millions of images. Here we have kind of, if you want one, but with spectral channels 220, right, if you take in this dimension. So it's not really very much, and this is of course a different challenge. So for all of you that want to play around with this data, it's online, this Rome dataset for instance, everything is on B2Share. In a specific format I would like to talk about just to get you the inputs a bit more communicated to convolutional neural networks and what other models are using. So this is B2Share tool where we put all our data. The convolutional data is not yet there, it's basically very fresh data that we get, and this will come also as well very soon. Can use persistent handles actually here for publication links into papers. So we'll see one of our journal, for instance, that we had recently just have lots of handles like that. So it's also something you face as machine learner. How is your data preserved? How you can show that you actually run the model, right? So reproducibility of your results. And with these kind of tools where you have a handle, independent of your location, you just put that as a handle in your publication, it automatically will follow suit where it is physically located, if it's in Ghent, Leuven or somewhere else. That's an active matter of discussions now in terms of data management, but affects you a little bit also as machine learning modeling. And by the way, if you go to B2Share, you see also the support vector models and everything we discussed last week there with runs and everything. So this is, of course, an interesting aspect. Now you're wondering why I'm telling this. Let's go more sophisticated even. Rome was a very toy problem again, in a sense, a benchmarking, if you will. So here we have more a kind of cutting edge, and this cutting edge is still one of the older cutting edges. So we will see tomorrow. I will bring some examples where in the moment the people are thinking about. Right, so here's the Indian Pines. We used that last time for the SVM, so there's basically no news around it. It's still from the Aviris satellite, one image taken with spectral channels. And basically it's mostly agricultured and wooded, so you would think like, oh, that must be a very simple task, if it's not a city anymore. But we will come to a point why that's not necessarily the case. The image consists of quite some pixels. If you look now that we think about, okay, we want to have all of this classified according to several classes, and there are quite a huge number of classes, as we will see. But the spatial solution, spatial already rings a bell, is 20 meter. Right? That means also when you think about the spatial property of the whole image, land cover, always a spatial property is something interesting. Hence, that's why we go at all for convolutional neural networks later. If we would know that there is no spatial property here to be analyzed as a pattern, then we would not use considering CNNs. However, the pixel-wise labeling is also something we should quote, was done here by Baumgartner. Here's the publications of them, how created really that kind of data. Again, it's a ground truth campaign saying what is pixel by pixel, right? And the interesting thing is, it is really a big label of things like way is mixed pixels, so there are also sometimes different classes on one pixel. just for the amount of classes, you would not guess, but it's 58 different classes. But these classes are also loaded, right? They're very unbalanced. So some of you know that from last week, we talked about unbalanced problems. So we have not enough samples for some of them. In this, it's a very challenging data set to use, because you always have just sometimes too little samples to get a class representation. Hence, of course, what you do, I have done that myself in one of the publications I did here in 2015. We just put the 6 classes out, which are, completely not really under in any kinds of representation, less than 100 pixels to learn from, right? So this reflects a little bit the statistical learning theory that we had the last time, right? When you have for this given pattern 100 pixels only, then you're kind of having not enough samples to learn from at that point in time with SVMs and feature engineering. So we see that we stick the whole 58 classes in the convolutional neural network. We don't think about this, if you remember. Feature engineering, we just let the network do the work. The reason why we do this is, of course, to help the classifier come in quicker to convergence and have a better accuracy in these ends overall across all the different pixels. So this is quite interesting. And of course, some authors also, it's perhaps just as a side remark, how you can also make your data smaller or ready for different models. You can, of course, remove here the spectral channels as well, so you don't go so deep in the earth, so to speak. You remove some bands. It's also possible to prepare the data. However, you see already it's quite different from MNIST, right? So this is just a kind of 10 classes. Now we have 58 classes. There we had 60,000 samples, quite equally distributed. Every number had a very good representation. Here we have very unbalanced classes, mixed pixels, so the land cover on 20 meters, right? On this, somewhere in the outskirts, really change. So in one pixel that you basically have in the spatial suit, you have different things. You have water and wave. You not only have wave, but there are different aspects you have to consider. Best explained basically in a graphic that we used ourselves, or a table, right? Where you see a little bit the training and test samples in the kind of different classes that we have. And you see only if you want to find a pattern around soybeans as a classifier, you have to understand what the classifier is doing, right? So we want to understand the land cover. And now you think about, we want to find a pattern where soybeans are. Right, you see soybeans are hell a lot of oftentimes combined with different areas of land cover. So this is already a challenging mixed pixel problem for a classifier. It's hard to determine, so hence different classes. We have rare ground truths, as I said earlier. We put them out, which have, let's say, not really somewhere 100, more or less. So you see still here and there very low numbers, right? Very hard to learn from. Although it's already cutted in terms of classes, right? It's just 52, not 58 as the original data set we're going to use in deep learning. So when you go there, and just for your kind of understanding, why is it so much a time-consuming aspect? It's again, you think about what models could help. Those that have been part with me in the machine learning tutorial last week, or that would like to know a little bit more about this, we use this kind of idea of using just the raw data set. Perform cross-validation, partly, or just train some models and see the accuracy was around 40%. Right? So this was what we're going to do in the neural network now. Based on the convolutional neural network this evening, we just throw it as a classifier, unprepared. While the other track was now the work of the PhD student, right? There's a kernel PCA, it's a kind of dimensional reduction technique, really to get the more information content. Then once you have finished this kind of manual interaction with the data, you have this extended STAP. So this is largely, again, this mathematical morphology approach with the trees. I said earlier, of getting the neighborhood involved and then cut the trees at different parts, so get different neighborhood information included. So you do this, and then you do another, kind of very, let's say, domain-specific approach, which is this non-parametric weighted feature extraction. But in the end, all more or less manual processes. And in terms of tooling for this max tree and so on, which we just parallelized in Jülich, for instance, just as a matter of research, this also had to be implemented in MATLAB and other tools, which admittedly were serial at the time, but still lots of work to create that concept. Hence the kind of 3 years when I say a PhD now got basically to this track, and instead of 40% that you see on this way, of just using the classifier with the raw data, he got something like 77% with me, what I will show you. So this is kind of a benchmark set out. So we did manual feature engineering quite a long time and got 77%. So you were all part of that game, those that have been last week with me in the tutorial. Right? So this is a kind of elaborate thing which takes a long time, and then once you have done this, you do now the work on the classifier, and you would say, although it looks balanced here, 80% of the work lies left, 20% rather on the other side, right? If you typical data project. If you want to play around with yourself, just for your information, B2Share again has all the data set if you want. It's a specific format I would like to come to in a moment, libSVM. Of course, a de facto standard format for SVM in that sense, that we have to change, right? So we cannot use exactly the same data set now for convolutional neural networks. We could do that, we can just transform them, but we have to work on that data. It's not digesting this information directly as a libSVM format. That should be a little bit carrying the assets that, of course, still we have to do some work, but mostly the work in convolutional neural networks is just preparing it in some form of vector matrix representation, tensor representation, of getting the data into the tensor libraries that we have seen in the deep learning libraries. So in terms of libSVM format, we have basically the first is the kind of class information that we carry, the first kind of index, and then you have feature, 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 feature. So numeric representation normalized, of course. And then you basically have your 58 classes program. We see sometimes are not all the features present. So we see here, there's this kind of low level number of features or kind of numbers maybe missing, which is like the difference between sparse and dense formats, right? So here and there, if there's a 0, this is omitted in certain ways. Right, but comes to the essence of what we want to show as a kind of idea that we hopefully see tomorrow morning when the GPUs have computed. So what we did now is basically last week in the lecture, as the conclusion, so to speak, of the machine learning lecture together, was this grid search. We kind of focused on the smaller part, but there were teams contributing to all of this accuracy. And what we have seen is, by doing a proper, let's say, cross-validation with the kernel parameter gamma, and the cost that you do in terms of using a support vector machine as a Riedel basis function kernel, you come to an accuracy of roughly 77% in the serial case, so that is MATLAB, requiring 15 minutes, roughly, right? And of course, in our parallel world, this 15 minutes is not really satisfactory. So we want to have that more or less interactive, a minute or close to a minute or half a minute. But what we do here with this is basically using the parallel version with 80 cores, for instance, or less here, what we used also on GoLet together last time. We kind of went down to a minute, roughly, in terms of computing. So this, of course, should remain in terms of accuracy, right? So this is serial, that is parallel. However, it's inherent parallel, meaning that the algorithm is parallelized. So that means, in other words, this one grid cell is already a speed up, right? Everybody can see that we have here now basically broken down the 14 minutes to 1 minute by not using MATLAB, but a parallel support vector machine. And this is, of course, interesting, but the most benefits in parallelization we took away last week was really the second approach, that we can basically have all these cells also executed in parallel if you have the computing power. So it's a two-level parallelism gain that you gain by using cross-validation HPC machines. Doing this, we can do basically all these grid cells in parallel. And that's what a typical machine learning expert has to do, right? He doesn't know that for this particular Indian Pines remote sensing is C100 and gamma 8. As you see, the accuracy kind of varies significantly. And this is a key aspect of doing validation, model selection. So which of the parameters are the best for my work? And then I can train again. And then you get, of course, much better out of sample performance on the test set. But these are things we discussed the last time about more general machine learning themes. We'll come shortly together tomorrow, again on validation, how TensorFlow is doing it, and Keras. You have seen that indirectly already. It takes 1/5 of that validation, or roughly like this, and then basically computes and do the model selection on this one before it goes to training, and then out of sample testing. However, it will be requiring a lecture we will come to tomorrow morning. Hence, the takeaway message is the first of all, the time is very interesting, but secondly, of course, the 77%. But in all cases, generally across all of them, we could say that all of parameter sets that we have here, which are roughly 9 hours, we break down to half an hour. Right? So this is the benefits of parallelization. That's why we also do here kind of a machine learning tutorial as part of a parallel processing team and center. Right? There are lots of games to be done. However, for us now, as a deep learning interested people, we are interested to beat that. Right? So that is now the benchmark. And this is out in the field saying 77% with lots of manual work before. So how we can beat that, doing automated feature engineering and so forth, will be part of what we have to do. Just shortly how the data is stored, because some of you may be tempted to look already inside the data and actually how it works. We use HDF5 now for basically the data that we have. It's a specific model which there are lots of workshops around it, so I cannot go really in detail into it. Of course, it's like 3 days just HDF, parallel I/O, and what's the benefits. But you can consider it rather as a kind of file system on its own within a file. So you'd have hierarchical, as the name suggests, data formats where you can store arbitrary types of data. And that's what we do basically when you think about the Indian Pines data, right? So, for instance, it's very well suited for storing different arrays, which is also interesting for us, storing the output of the model maybe, and different records and so on. So this is all things where there is already a specific format, which is different now from the libsvm format we discussed last time. And some of you already touched this data with the clustering data we had last week, right? Where the HPDB scan and the point cloud data set, this was also in the HDF5 parallel file format. However, this is now available to you and you should take a look at it. So let's look all together, because there's now careful consideration that we have to look to, and that's why I need everyone's attention before we go in. We have limited number of GPUs available, as you know already. Which means please don't use this full data set. There's only one gentleman that does it at home, that's fine. And I encourage him to do so, to really understand now the benefit of going to a new GPU. But for you all, please wait until the tutorial is over. I think there's still a chance of having this done here on the weekend if you like, and if you're really interested to do the full data set. The full data set means what I will present a little bit, so why we got good accuracy, how long it took, what are the results and so on. I will still have that in my slides. But for you in the training, please don't do that right now, because if you do that, it will take very long time to train. I think it was 12 hours, Kenneth, right? Something like this. 12 hours to train.
No, 16.
Or 16 hours to train. And with this, you block everyone else also, and you have no time for doing more interesting stuff with us here in the tutorial, because we downsampled a kind of data set for you, just for the tutorial. So please use a small data set that we will explore now, right? So everybody maybe just log in now to the Ghent machine and look a little bit on what types of data is there in these directories. And you will see here an HDF5 file. And an interesting takeaway message I want to demonstrate with that is the following. So please, you can also go all to this location, right? And maybe look into the file, into the HDF5, and see some interesting aha message. So we are in apps, Ghent, tutorials, deep learning. This time we're not anymore touching the MNIST that's happily running in the background. And of course you can still use it and change layers and experiment with it. There should be a data directory. Just for the matter of sake of see full, how big it is, you see quite some very big data set, which is partly related also to some of the data preparation we do, but still it's a very big data set. All the 58 classes, use that after the tutorial. That's why we prepared for you the small set. And it is just the 16 classes, and as you can see here, largely orders of magnitude smaller. Not only in terms of classes, so it would be much easier to work on this data set for the classifier. It's also much, much less data to digest for the TensorFlow/Keras framework, right? And with this, automatically less to do for the GPU. That's why the K40 can handle it. We have tried it, and I think it takes around 3-4 hours. What was the last?
The small one?
Yes.
No, half an hour.
Because we used the 2 GPUs. Yeah, exactly. So we switched between using 2 GPUs at the same time. Exactly. Then we were able to at least have half an hour. And this is now opportunity for you to play around much more than with a full data set. Right? It's an order of magnitude, just half an hour runtime. So that's something more where we can get scheduled. However, remember there are just 5 K40s. And I think on the K20 it significantly takes slower, right? I think like that's probably more in the direction of 2 hours or so. So, and you basically have no input in that process. It will be part of the scheduling, right? So in this sense, handle this with care, what we do right now. Perhaps for the learning experience, it's interesting to do, for instance, this hat, what I usually also do with my students in class. Why is that? Anyone has an idea why I cannot look into it? Okay. Exactly, right? So it's a binary file format. Why should the computer as a supercomputer waste time of transforming some binary representation that the computer anyway has into a human readable format? Right? It's just again time waste. Of course, it's nice for us to debug here and there. And for those that would like to try out, there's a HDF5 viewer also, right? I will point tomorrow to it that you can use. We don't have really very much time here in the class to look at it, but all you will see basically is the data in terms of 16 classes in this one, and then having different, let's say, pixel values in the different dimensions we talked of. Still, the interesting takeaway message of that is it's not feature engineered, right? Those who had with me last week, we looked at the raw one and we looked in the pre-processing one. The raw one has 40% only. The pre-processed had 77%, as we just seen, with lots of massaging. So let's go to the next level, which is hopefully more percentage of that. Right, so now that everybody can access the data, and speak now if you could not access the data, right? So you know where the data is, right? Okay. So we look now on a video, and then we will do a little bit the idea, basically how we created the model, and then we do already some practical so that we get the execution done. Perhaps just before that you understand what remote sensing is, we have a nice video about that before we start the second part.
Well, I like to tell my students that remote sensing is the science and art of determining what's there without being there. Okay. So one of the things we do is to look at reflected sunlight. And there can be reflected sunlight giving us colors that we can't see. The visible part of the wavelength region that we see is very small compared to the total amount of reflected sunlight that comes off the Earth's surface. So if you look at all of that, you start seeing an enrichment of information about what it is you're looking at. Now, if you add to that the thermal infrared, which isn't reflected sunlight, but is heat emitted by the object that you're looking at, then you really do have a wide variety of wavelengths of light, electromagnetic radiation to look at. And then you can start answering the question, what is it made of? Because spectroscopic techniques have been used in laboratories for decades before the first remote sensing satellite went up. And they would use it to determine the chemical composition of things that had an unknown composition. Now, this kind of information is looking at the Earth in many wavelengths of light, which is multispectral. It means many wavelengths. Hyperspectral means very many wavelengths, or as the French say, beaucoup wavelengths. That is what you need in order to determine the chemical composition of what's there. And finding out chemical composition is far more useful information many times than knowing the shape and size of the object. For instance, if I had the spectrum of the paint on your truck, 1 pixel the size of your whole truck would let me identify that truck, because I would be able to look for the composition of that paint. It wouldn't matter that I couldn't tell the difference between the cab and the bed, or that it was from this angle or that angle, or that it was longer than it was wide. I don't need any of that. All I need is that chemical composition of the paint. And if it is a unique paint, I've got it. Now, a lot of times it's not so unique. It might be a paint that Ford Motor Company uses. Another one might be a paint that Toyota uses, or maybe they only use it on their Land Rover. Okay? Whatever unique chemical characteristics there are out there to look at, that's what you can go after with multispectral remote sensing.
All right, so much for the application field. Being a little bit in that field as well, I would encourage you to study it. It's a quite interesting area to be, and it's much more newer satellites with much more better resolutions, more spectral channels, beaucoup wavelengths, right, as we heard. Before we go off and go to the practicals, is there any kind of question related to the general approach we had in terms of feature engineering and SVMs, or any questions related basically to our application field, remote sensing, Earth observation, and so on? Going once? Twice? Okay, so if that's not the case, in order to save time, we will not explain the whole model in remote sensing and then compute. We will first compute the Python script, and I will explain while we're computing again the Python script, right? The same approach basically we did with the hidden part when we now go to the application domain. So we do use the KU Leuven though, now in this example, which means you all should now go basically to Golet and from there to the Leuven system, right? As we learned. If you remember, SSH login at hpc-leuven.be. It should be in your history if you do, and then scroll up using your upper part, but I also will show you what to do. Essentially, everybody should do that. SSH login.hpc-leuven.be. Anyone who cannot do that right now, because we want to submit now, okay, there's some problems. Just raise your hand, because now it's important that we today submit a couple of jobs, right, before the end of the day. Any other problems? Anyone? Okay, the login works for the majority, great. So let's look at it. So, being in Leuven now, remember still this delicate issue, just again as a reminder. Even if it's only half an hour, we don't have so many of the GPUs available, right? So you're encouraged to use them now as part of the training, but please don't use it perhaps as you do in the CPU case, so just run a job, run a job, run a job. Just make, let's say, a couple of them over this evening, if you like, and you will be scheduled here and there, because we also more participants. As we heard, it's not only the 5, luckily the K40, but those are significantly smaller, older, and so it will take more longer time. Right? Once again, careful usage please, but still of course we should use them to one degree. The particular files we need are those that should be already in your home directory. Right? We prepared for you also the full, yeah, but in the moment, please focus, and for the sake of the tutorial, the small one. When you're then at home, basically on Saturday, Sunday, if you like, or next week, Monday, you can still use these kind of full and try it out, or use it on your own GPUs if you have one, like one of the participants here, for instance. Right? Of course, try to use it. The data is open. You can use it. The structure of the GPU Python script is there. You can experiment with this, and we will go through it step by step how to do it. And then basically have also the job script here that you usually do and use. So everybody from you should basically do now just a QSIP, because that's a major important thing with this one. Here is the reservation included. So let me check. That is a Python. The job script is... This one is the one to look at. Now the interesting thing is that the reservation is already included in the file, right? So when you do the QSUB of this job, don't do the reservation again, as you did before. Here it's already included in the file. And the rest basically stays almost same. We add a couple of things more like scikit-learn, and here a kind of array for specific handling. But the rest of the idea of the job script remains the same. However, the key thing here for you mostly is, you know, we keep basically the reservation inside the script. And then, of course, we do this usual thing with creating a working directory and so forth. And the Python script basically come into the game. Then we basically look a little bit on the input file. We copy that. If that is okay, because it's relatively small, if you remember. Think about if you do this with a full one, right? It's considerably more data, 12 gigabyte compared to 350 megabyte, right? If you do it after the tutorial with a full data. This usual thing, Keras, is a backend called TensorFlow, you know that already. A little bit we want to know how the GPUs are used, so here's a kind of information about the GPUs and areas that are there. Gent has no GPUs right now, so we are now the Leuven system with GPUs, so there should be something coming out. And then we run, basically, as we know already, Python. But with the new Python script, I'm going to tell you more about while we're running the job. So right now, basically what you all should do at least once, perhaps in a team or so, or two, let's sit close together, or if you work alone, that's fine as well. Just do the QSUB, of this, of the job script, of course. So of this job small to GPU. Again, now it's important that you are in Leuven, otherwise it will not work. And observe with QStat again what's happening. And as you heard, with 2 GPUs used, it will be roughly half an hour, right? So then we should see the first results coming. Of course, it depends now if you're scheduled and when you're scheduled, right? So this is, of course, a kind of second variable. That's why we keep it now open for you, and you can submit. Also, maybe in the evening, if it's 7 o'clock and you would be interested of resubmit it, please do so. Tomorrow morning, we will analyze these results that come out, and we'll discuss it a little bit more in terms of challenges, regularization, validation. Right, so please do that now, and if there's a problem occurs, raise your hand directly, right? We have a couple of gentlemen here that could help. Okay, good. Yeah, welcome back, and also welcome back to our online audience as well. We had some technical issues here, but before we wait, let's say the last time of waiting and waiting, let's do the experts do the work and find out where the error is. And we go a little bit in proceeding understanding the convolutional networks. So here and there, when we see that the technical issues are resolved, we will come back to it and then submit our jobs. Otherwise, we will do it tomorrow. We have still a whole day tomorrow, right? And with having a half an hour job, we still can do interesting things tomorrow. Let us look a little bit on the application domain now, because we lost already quite some time in looking a little bit what we want to do. If you remember, classification is still our method of choice. However, take away the message, we don't know pixel-wise classification, right? We change the nature of the classification basically from MNIST now to pixel-wise. And this means we have to also look a little bit more closely what we do in terms of data and how we prepare the data. And this is one of the convolutional neural networks that we used and that we created. And by now you basically can interpret them also very well. There's not very much, let's say, a mega difference between that. You still have convolutional layers. You then do, your feature maps, you have max pooling, and you do that a couple of times. In our case, it will be 3 times. And that is largely what you see in your Python script. We will come to that and discuss it. However, a little bit is interesting how we prepared the data. And if you remember now that we basically the last time had this 28 by 28 MNIST pixels, what we did here was we basically created a kind of window tensor. And this means we have a 9 by 9 window, so to speak, on our input data, which was, the big pixel image. But we just pick the middle pixel, so to speak, where the label is existing, and include the spatial properties around it. Now that is this dimension, 9 by 9, hence the name of the data you just used, basically, in the HDF5. Of course, that is no one telling you that you should do that this way. You have to experiment, you have to find out. But of course, we know that capturing the spatial data somehow is important. And now if you compare that with a libSVM format, we didn't have any spatial relationship anymore except the feature engineering. Right? So libSVM format, if you remember, was line by line, 1 pixel. There was nothing telling us the neighborhood pixel is line 500. So that's something which is quite important. So here we have now a spatial property of saying all the pixels that are close to this kind of middle pixel here will be included in the input signal we give to the convolutional neural network. Then the other aspect, you remember the MNIST dataset was not very rich in terms of features. So the depth that we had essentially was grayscale, not even RGB. It was black and white or grayscale green. And here we have the 220 bands, if you remember, from the satellite, giving us different spectral wavelengths of light. Right? So this is all features on the same pixel. Right? And of course of the surrounding pixel. So we kind of have this little cube, if you want, from the big cube point, cut it out and give it as a signal. That's what we prepare basically for you in this HDF5 file. So what you have is basically going through all the data that we have in the Indian pines in that fashion and include basically this kind of window tensor. We do that to preserve the spatial properties mostly, because otherwise, if you remember how convolutional pooling works, it looks on the neighborhood, right? If you don't do it and just put a pixel in, then we are, of course, some trouble, right? And this is the kind of first takeaway message. We have to prepare the data differently, like in NIST, for example, and we are much more richer in terms of features in that space. However, the idea then, you see, is not anymore 2D then, it's getting 3D tensors, right? So what you're flowing at the arrows basically is then the kind of multi-dimensional tensor that is in terms of weights trained and so on. Hence it gets much more computational complex. And don't underestimate this little fellow is loaded, right? It looks so simple here. This we do 3 times. We send it 3 times through a convolution in order to get a good accuracy. Secondly, if you remember, we kind of, for your data set that you try out in the moment, it just has 16 classes. So we in the full data set, that is 12 gigabytes, you have all the 58 classes, right? Of course, with this, we have to do a little bit difference in terms of what would be the kind of output probabilities here. So we have just 16 classes, so we would model that a bit differently. We will look that up in the script. However, the good news, perhaps, for some of you, if you look just like here, what does it remember us? By now, hopefully, the majority of you know that. What are the last layers of a convolutional layer? Yes? Sorry? What was that?
The traditional network.
Exactly, yeah, artificial neural network, right? So that is basically what this, we have fully connected layer dense. the same way we had in the 2D, softmax layer activation function to get the probabilities, this time across 58 classes. And of course, as we've seen, this mixed pixels and so forth, there might be the probabilities not that clear, but still they add up to 1, and we can determine what would be the best probability of a class. The flatten here is necessary. It's kind of an input to the neural network, if you remember, kind of simplifying that we have a 3D structure somehow coming out of this, which needs to be flattened in the sense of having a one big vector as an input to the dense neurons, right, as an input to the neural network we had in the beginning of the lectures. So in a sense, you see what you're playing around with to get this is a little bit preparing the data, but not really feature engineer it. Right? What we did here was just include those pixels which are anyway there. We didn't modify them, we just include them. And the spectral channels have been also there. There was also no magic. Right? Compared to the SVM case, we worked a lot on the data, prepared that as you were listening to the last lecture. So this is the first element that we did. And of course, an interesting thing that we get very good results without any feature engineering. So let's go there a little bit. This step we have already done. Basically here were some problems, but the general meaning of the script, I think some of you know from the job script already, but let's go a little bit more into the modeling. So what is basically what we have to do in terms of executing, for instance, to the GPU. That is one interesting aspect that we have as terms of changes when you think really going to a 2 GPU problem here. You have to specify a little bit in this kind of Python script that you're now going to 2 GPUs. So you see a little bit, it's not really completely transparent what infrastructure you use below. Still, you have to tell Keras what you're doing in terms of parallelization. That's a little bit here an interesting aspect. And then you have a parallel model that you have to compile, which you have also basically in your Python script there. And then here and there we had also, of course, a parallel model fit in terms of a normal fit. That's a little bit of change. But the overall idea of our test samples, of the batch size, epoch, shuffle, and so on, stays the same. Right, so it's just a cutout, basically, of the changes related to the GPUs. Just because if you now want to play around with it on the CPUs here in Ghent, for instance, or somewhere else on another cluster, you can still do so. But once you move to the GPUs, you see here, you have to do some changes. So let's look at the model in terms of Keras. Now it's getting interesting. But on the other hand, I think you will agree with me, it looks quite obvious in a way. We create again a kind of model function really that takes here the input shape, the activation function, the number of classes. And then we have a similar approach that we did in the convolutional neural network for the MNIST. But of course now a bit more sophisticated of just adding the convolutional 3Ds as we discussed. Now, as we also said, it's a 3-dimensional kind of cube we work on. Of course, our kernel that is doing the convolutions is now a 3D convolution. So kind of we do all of this, and that's why we basically have also the kernel size not anymore like if you remember 5 by 5, for instance, one of the examples is 3-dimensional. So we go now basically again through the whole data that we have. But the neurons, in a sense, are now kind of 3-dimensional. We have a really interesting tensor problem here, and that we go through the same way I discussed basically in the 2-dimensional. But you can imagine now getting the dimensions, this needs much more time to work on. Then the activation function will be taken for that. We take the pooling approach the same way we did in 2D, basically now in 3D. And you can do different poolings. You give in the size to which amount you want to pool, and for instance here we pick the max pooling, but you can do other poolings as well. Again, the strongest signal in terms of a 3D block will survive, right? And with this we significantly decrease the number of weights again. So in a way you have now a kind of 3D subsampling from your surviving signal and tensors that will lead them into the next layer. Here and there for the kind of format and for the going through the pooling, you will see it will not fit completely to the kind of dimensions. Hence, we do some padding here that we basically fill the remaining pixels And this is a zero padding, so basically just zeros will be fitted there. Also here are different padding strategies that you have to find out, you have to work with. Some of them that we have heard the last time was sane, for instance, another padding strategy. And then we do that 1, 2, 3 times, basically, which is alluding to this kind of structure here, right? We do the max pooling, convolutional, max pooling, convolutional, max pooling, convolutional 3 times. So this is interesting. Still, to find out exactly how big these parameters are is not something very trivial, right? You have to work on that. You have to see what are basically good properties around that. Of course, we see a little bit when we have a 9x9 window tensor that this might be a bit related. So some of these things you should consider when creating a convolutional neural network in 3D. Then we have discussed that the last layers is really just what we did before, the hidden neurons, in the dense kind of fashion, in order to prepare the signal really to a classification, which brings us then to the softmax layer at the end, and before some kind of flattening to give that in a kind of one neuron vector structure into the neural network. And which comes out are the output probabilities of the 58 classes. So return the model and the function is complete. And this is really something where we got in Jülich on our machines like 85% accuracy, right? You see, basically without doing anything on the data, we got 8% better. And this is a remarkable case. However, it's a little bit loaded in terms of sampling bias. I will allude to in the challenges tomorrow. Because some pixels are used for training and testing, so it's a little bit we have to be careful about. Anyway, the result in itself is quite of a major jump. So from this we kind of learn that we have to a little bit look on the spatial properties when we give that to the CNN, just as a conclusion what I said earlier, right? The libSVM format is a nice format, human readable. HDF5 is not, you have experienced it. Still it captures the essence of the 9x9 spatial property. If you put something without the spatial property basically in this kind of spatial train, or basically spatial property preserving neural network, there is some kind of problem, right, of not choosing the right model necessarily. It will not have really benefits of using the spatial property. Receptive field ID, the kernel learning, it will be all different. So take into account this, because the lib format, libSVM is really pixel by pixel, no relationships if you don't encode it in the features itself. Like we did with SDAP last week with the feature engineering, right? There we have, through the features, the mathematical morphology and the enabled pixels involved. Hence, we use the HDF5 format in a 9x9 case, and we tried different out. It's not that we said like 9x9 is basically the way to go. Hence, you still have to work a little bit on the data and prepare the data, but it's in no way working so much on the data like PCA and so on. The message you already, I think, get. Still, I think it's important to mention, remember that we just have the label for the one in the middle, right? Is it a forest? Is it a river? Or so, and the others are, in terms of a label, not so much important in that sense. We give it just to preserve the spatial properties of including better signals. And that's what all the neural networks are, right? They kind of transform the signals from layer to layer. And it makes the signal stronger when you have the spatial property, as we know, and it makes also the chance of discovering a forest that is here somewhere else. As you remember, this sharing weights in the feature maps. It is a very important concept here that you can, again, are location independent, and what probably is one of the reasons why the accuracy gets better. Right? So this location independence, and this is of course very interesting to do. So wherever you go, perhaps consider also HDF5 in the application domain. Some use NetCDF actually also, and these are two parallel file formats which are often used in the scientific and engineering communities. Now let us come back a little bit on the imports and on the whole script, just because we use now a bit more elements, right, of Keras. Now it's more interesting to look what other thing we have to import. Although it's not very much, let's say, different. Tomorrow we will talk about regularizers. Today we talked already about optimizers, these kind of things. The layers now are a little bit different. We have the convolutional 3D in terms, instead of 2D, dense, max pooling 3D. You see, basically for all the types of different tensor dimensions, there are different implementations in Keras because the underlying library of TensorFlow has to also work differently. And with this, you come to then regularization approaches we talk about tomorrow with dropout and the challenges and so forth. Then you see some callbacks, what I also want to say here as an interesting add-on to this. Now think about you trained a network and we said something like the full network takes 12 hours, right? Here on a GPU to train, or 2 GPUs really. Then what happens if after 6 hours there is a power outage or the cluster goes down or there's an LDAP problem as we maybe observe right now or whatever problem it is, then all the success, all the weight training is gone, right, that you had previously. So think about this, that now basically you have the problem of everything is lost after 6 hours, 7 hours. So there's a checkpointing mechanism. So who knows about checkpointing, perhaps from some other areas? So simulation scientists do that a lot, you know, weather forecasts and the people that have lots of physical models that run 24 hours, 36 hours. They save the status again and again to disk. And what we do, for instance, we do it every 10 epochs. It's something which you can steer, but there's a possibility, and actually it's also implemented in Keras and also in TensorFlow underneath. So when you go to production runs on your data, what it means is you can store your weight optimizing process every time. Because we have a very limited time here in 2 days, I cannot show all the details, right? So these callbacks here are basically a script we also put in, which you can look in to the scripts directory. And there you will see basically the whole idea of checkpointing, that you save the history of the weight optimization process, and you basically have operations that you can use to do it every whatever epochs you find useful, right? But it's a nice property if you think about you have very long running jobs that suddenly, you know, the cluster has a problem. You just come back to the last saved one, and with this you have a good chance of getting, you know, quicker again done with the jobs. Right. So there's a timer that's not so interesting here. Very important TensorFlow for some other aspects I will going to show. Multi-GPU model, we have to include this if you want to go to different GPUs, not only one GPU, we use 2 GPUs. There's a confusion matrix which tells us a little bit around the foundation for accuracy and scores and like that we're going to work on, largely dependent on the evaluation of the models. And we use here the scikit-learn a little bit to help that modeling. Still, it's a Python code, right? We can combine everything. We don't necessarily bound just to use Keras or just to use TensorFlow. We can also include other interesting libraries like here. Right, so when we look now on the main program and the parameters, that's also interesting for us because now we had the function in the beginning, but of course we also need to feed it somehow with our, let's say, parameters that we train. And there are some of them that I cannot go because of time reason in today. We will do that tomorrow morning in the challenges, where, for instance, of course, these are very simple now. You already know the game. It's like 58 classes, so that's important for us. We see the epochs, the batch size, the window size we discussed, right? Very important for us, what's in terms of input, how that looks like. Here are certain properties, learning rate, momentum, decay, right? These are all things which drop out. We will think and discuss a bit tomorrow. These are regularizing aspects which here and there even have the chance of, you know, improving on the accuracy. This would be too much today. The loss function is here the mean squared error. The activation function is the rectified linear unit that we already discussed. And here the SGD in context, basically with the learning rate we set here and different momentum and so on. Right, so this is something interesting. So this is now a little bit more going into a really production setting, right? So this is a more cutting edge example than MNIST and already interesting to study. So when we look further how we have to, you know, pre-process the training data, it's a little bit like better to be viewed in when you have the visual representation, right? This is now a bit let's say, TD because we load the training data, of course, from HDF5. And this is something where, you know, we have already like libraries that help you with that, so there's no point of going manual through this format. There are usually always APIs that get you data from HDF5 out. And then you have some preparations here, normalizing factors again, using the standard deviation, and basically just preparing the data for the model. Again, a reshape, similar like we've done also with the MList. So this is all kind of preparing the Windows tensor really in order to go basically towards the Keras environment. And here, of course, we want to take a little bit the time and everything and have different shapes. But essentially what we do is exactly this. We kind of prepare that now for 3D input, right? And this is, of course, something coming out of a HDF file, a 5 file that needs to be done once, but it will not something that you spend, let's say, lots of hours in terms of feature engineering. You have that once prepared and you reuse it many times, right? So this is again another step in pre-processing the training data. Now the interesting part happens when we come to building the model. So it's of course reusing our function and the compilers. So this is basically the model standard that we create. This model standard doesn't mean from Keras it's a standard. It's a kind of, let's say, indicator for us here in the tutorial of saying, this is for us now the standard we do today, because tomorrow we will try out regularizers and so on. And these will be not the standard models, right? So the standard by no means is anything special. It's just a function name that we had basically defined at the beginning and that we just reuse here with the kind of things we just discussed, input shape, activation, and the number of classes. This example is, of course, for the full-blown set, right, for 58, right? There's this other Python script that you have prepared from us with subsampling, saying it's 16 classes and using the other data. This is now a real production problem if you want a real application problem. And here's a little bit what you can do in terms of randomization and weights. I skipped that a little bit because we have not so much time and we probably want to resubmit also later on another job. Just perhaps then some results, because now you would be interested, okay, by creating this, or before we go that way, maybe is there any question related to the 3D convolutions and just going multidimensional? And once, twice, okay, it's always getting into at the end of the day, and we have lots of snow outside, so basically also we will probably finish very soon, but we hope to get the job done, or at least submit it before we leave here the room. So what we did in Jülich was exactly this. You see, in order to get to a quite high accuracy, you have lots of configuration options. Some of them we will talk about tomorrow, you know, learning rate, the rate decay and things like that. But still, this is something to kind of always present if you want to show basically why you got high accuracy, how is the structure of your network. That is something what you have to really put normally in your reporting. And some of the things we discuss tomorrow. You see here also we have kind of Tesla that's a little bit more advanced on the core K40. We have the K80 on Eureka and the P100 on Neuron. So they are kind of very fast GPUs. That's why we could compute the kind of full one a little bit faster, right? So, of course, here and there, MATLAB was used for the preparation for the data. So here's a data missing. So this kind of things you have seen, like cropping the image, for instance, and preparing some of the data for the small-scale example is basically something which we use still all traditional tools, which are very good in, you know, switching between different formats and so forth. So it's nice to combine these things, parallel computing with serial tools here and there, when it's possible, especially for data preparation. I personally also use Riedel, for instance, here and there, or R, so different themes of R have nice CRAN packages. In the serial world even, just to prepare and check a few things, and then do it in parallel. Right? So this is nothing where you say you're just bound to this particular one tool of Keras or TensorFlow. As we have seen, we can use scikit-learn. They have interesting evaluation packages, as we see, which makes sense to combine to make the point that you do in your convolutions. in terms of the versions here, you should be very careful because our experience of using now very many clusters for that is, it's highly, as we see right now, it's not, in the moment working with the practicals here on GPUs. So this needs to be specific versions with specific kind of GPUs. Here's lots of problems in terms of the very old GPUs and very new TensorFlow or very new Keras, it might not work, right? The CUDA libraries are different. It's lots of system incompatibilities that we explored, and if you even build it from source here and there, it's still very much of a problem. So it's good to have system administrators that really help us in really setting this up for us, and don't underestimate the work that is actually going into that. And as you see right now, there could be also other issues, like for instance just the security, the system accounts, whatever, which are not even depending on these problems, but which are related. Right, so here and there the automated usage of CPUs, there's no point of implementing CUDA yourself. You don't have to program CUDA. TensorFlow has already everything via the cuDNN library and uses this just straight off the shelf. All you have to do is indicate that you actually want to use the GPUs, right, as we have seen in the script. Now in terms of training accuracy, that's now interesting for us as an aha effect, because if you remember what I discussed in the first part of the lecture was we have kind of an SVM comparison, right? So we set the benchmark and said, well, with cross-validation and all the manual feature engineering, we came up to 77% accuracy, which is here, right? In terms of this is training and test. Of course, if you remember a little bit from the last week, we said what we are interested in is out-of-sample performance, right? You can measure the in-sample performance, which is this, your training set. And you can also measure the out-of-sample performance, which is this. So this is, of course, usually a bit lower. So it means, in other words, we want to generalize well to unseen data, right? And of course, the training set, the data that we know, it will be always better. And also in your output from the jobs, you will see the accuracy usually of the training is very high, but it significantly drops in the testing, right? And this is something what you see in the job outscripts I have also prepared here for you. But this is now, in terms of, the kind of benchmark, interesting, because we took lots of time to do the manual feature engineering, but we just put the signal as is. With 58 classes, all we did was this window tensor of 9, basically 9 by 9, and put that into the convolutions, and it created the features themselves in the different convolutions, and in turn created them after a number of epochs. Of course, this takes some computing time, right? But also we have seen in the SVM, it took some time to do the n-fold cross-validation, right? The 10-fold cross-validation we did as a group at the end was also not something we did just in kind of 1 minute. Here and there took time because of the fold to be very sure what would be the out-of-sample estimate. Right? With this then we could do the model selection. The same is done inherently here with the validation set, so we kind of can be sure that this is almost right. However, we have a small sampling bias we discuss tomorrow in the challenges. Hence, this is interesting in more ways than once. Lots of time savings and lots of interesting aspects in terms of accuracy, because we have like one win 7 or 8%, maybe another million we get from Netflix if we use the system on their data. Right, still you see also, and this is another point I wanted to make, when you do your jobs at home and run your jobs in the tutorials, think about sometimes cutting epochs. Right, so you think like what's happening now inside an epoch, if you remember from the beginning of the day, I hope, here and there the batch sizes, so you do in each of the epochs, the batch sizes, you train, you optimize the weights, lots of computing time goes into that epochs. So just having the 600 means it's already used lots of compute time. And is it really worth the accuracy? Right, in some of the cases you might go and say, maybe we can cut the epochs, and with you save lots of computational time of rare resources, like for instance of the GPUs, which are very attractive right now. Everybody wants to use it, hard to get lots of time on it. So maybe here and there you should look on kind of using, like for instance here scikit-learn or other approaches of measuring this a little bit. How is your behavior of the training process itself? Because this, enables you then to say, for instance, as we also had done last time, early stopping, of saying maybe 500 epos will give us almost the same accuracy. However, not do it to the other extreme of saying cut away too early. Right? This is of course another point that doesn't make sense, and if you know a little bit about statistical learning theory, then we don't learn enough, and this will give just bad accuracy. But here we could think of just cutting away maybe a little bit on the epos to get the same accuracy out. Right, okay. So in terms of classes, that would be the next question for us. Right, so when we think about, we gave now the raw signal in, isn't that kind of strange in a sense? Because we know from one of my lectures, if you remember, we get 6, for instance, out. We sampled 6 out because there were just 100 pixels to learn from, and that would be very bad for a classifier to learn from. And so you see, in a way, that this is still true in the artificial neural network here, or in the CNN, a little bit with this histogram, which is nothing else than the kind of relatively size of the class, was also basically the accuracy. And you see in some of them the accuracy is just bad. In other words, even if you have, let's say, less sample to learn and having now a powerful convolutional neural network, it will still not help these classes to learn well. However, interestingly enough, what would be in other cases, like more traditional classifiers, they will disturb the classifier, but as we see with the high accuracy, that's probably not the case. The accuracy remain highs in many of them that probably have, relatively size also very high in terms of representation. And in some of them, there's, even the size is not so very well, but still very good accuracy that we can show. However, you see, there are these learning theory-like, that is very beautiful, because you see, learning cannot take happen. Go to an exam and you get, material that you have to put in an exam, or work by a professor in an exam, material you never know, right? It's something like this. It's like 100 samples, almost nothing. Explaining this. And this is, of course, something to check here and there when you go to practice, the class checks and so forth, to think about when you evaluate your model. Don't consider always accuracy is all what you need, right? Also think class coverage and so forth. Right, so you can also draw a map. That's also nice, awfully interesting. You kind of, can kind of repeat what is a ground truth. You see that here, for instance, just to make the point where it is now correctly classified or incorrectly classified, and make a color map. Of course, in the end, these are all real locations on this map that we had as ground truths. And here it's a nice area to see where perhaps there are sometimes problems, or where the kind of incorrectly classification takes place. Could also mean we send another ground truth campaign somewhere to do perhaps better ground truths, like here, if it is possible at all. Right? So if you think about large scale will be there also tomorrow. What we always think about is now one image, one spectral channel, one picture of the satellite that you heard in the video. But basically what you think about now, we're interested in land cover, how it develops over time. How was the land basically 20 years now used in around Leuven, around Ghent? These are questions which are also very interesting for planning cities, for planning infrastructure, and this is what you want to classify over time, satellite time series data. And then you can imagine there's lots of big data, lots of computing time required, which is just the next step. Basically, once you have settled with this, now going more to the soccer watch. You have a time series of images, right? The soccer watch is not static, it's very dynamic, and the same you want to do with land cover classification. So in this sense, it's just the tip of the iceberg, if you want, for the next 5 to 10 years to study. Right, so now is the idea of checking the GPU runtimes, and what is the technical team at the back? How we are?
It's a general issue in Leuven, and it should be fixed in the, let's say, next 5 to 10 minutes.
Okay.
It's not specific to us, it's everybody in Leuven.
Right, okay. Right, you see, we still unfortunately have the technical difficulties, but in the end, we can look a little bit what you can expect, right? So let's wait another 5 minutes. Or 10 minutes, and then at 5 we will close, I guess, because also the snow, the people want to go home, and we come back tomorrow morning and do some runs, and then the error will be hopefully fixed. So you see what you basically can expect a little bit when you have the output from the data. Here's again a kind of small data set that we have seen. So you will see it as just 16 classes. And the accuracy here is an example. For instance, you see here is a training accuracy. It's quite very high, like 98%. That's not what we can achieve. But the testing here basically shows us like 73%. However, the point I also wanted to make is here the new loss is bigger. You see saving the model here and there, of course, means like when you got to some kind of optimization process, it's not always better. You could be stuck in local minimum, then you jump to the next area, then you have a better minimum, maybe towards a more global minimum, but then you catch, so it's a kind of SGD problem in a sense of going up and down a little bit with these numbers. Of course, over times in the epochs and over time in the batches, you should go lower. But here's where you can expect it. The output will be very big, right? When you look at it, maybe later today, if you're interested, or tomorrow morning we together. When you run it, you see lots of output from the epochs. That's why I put you here some kind of aspects you should think about. Check a bit what's happening. That's always very important. You should know what your classifier is doing. Here we said it's 16 classes, 220 kind of channels. The next dimension to the problem, and then the window size 9 of the spatial properties we discussed already in the images, right, in the visual representation. And here you have nothing else than the thing we already created, so to speak, in Keras, right? So it's a convolutional 3D, and max pooling, and this several times, as we discussed 3 times before we come to the flattening, and then basically the dense. However, before we try the next practical, there's one small question I want to do. And maybe, let's see, as an exercise, if one can answer that. So we have the small data here. And this is the kind of structure of the network. So has someone an idea why in the small data there are less parameters at the end than, let's say, if we look at the full data at the output? Right, you see here, that's a small data output, which means 16 classes, 2000 parameters at the end. And we have the full data, 58 classes, 7,400. The rest of the network, you see, basically stays the same. But why is a different number here? Exactly, right? If you think about what we discussed this morning, exactly correct answer. We have more output neurons. With this more output neurons, so to speak, through the softmax, we have more parameters going to that, right? And with this, we basically have more parameters we have to train, we have to work on. It's the very, very last layer, if you want, that we see here of the neural network with the activation and at the end. And the interesting thing I also wanted to show you, if you look a little bit on the parameters in general, it's not a big deal because you use the same network for the small data as for the big data. So the change is largely really at the output neurons, having 16 class probabilities in softmax compared to 58 classes probabilities. However, if you now remember a little bit from the hidden neurons that we had in the beginning when we did submit our jobs, the number of parameters was basically here an alarm bell by overfitting. Right, so it's maybe indicating us a little bit lots of parameters, let's see. But still we see also that the accuracy is very high, so we maybe overfit. Right, and this is a little bit we have to discuss tomorrow in the challenges, lecture 4, where we come back a little bit to the problems. But this is what you can basically expect. Again, the full data, please don't use that this evening, and just do that when this tutorial is over. Then you basically have lots of free time to use that and can explore that. No, but what we are interested in is, for instance, this run then that we had here, where you see the in-sample performance on the training set is 97, so that is a lie to ourselves. But if you see unseen data you see we get an accuracy to indeed on 83 on the full data. And if you remember, 77 was the best we got with support vector machines, right? And now we have really 80, 83 point something in terms of accuracy. In a way, that's really the main message I wanted to bring today. Of course, I hope we can still submit maybe in 5 minutes. But if that's not the case, we will discuss it tomorrow morning and we'll submit tomorrow morning. We will stay here for 5 more minutes in the room, definitively in terms of checking. But of course, if there's time to go, we see you tomorrow morning with lecture 4. Thank you very much.